Okay, so we know reaction rate means how fast the reaction is occurring, and we know that changing the concentration of reactants often changes the rate of reaction. So we need some way of showing this relationship between how changing concentration of reactants affects the rate of reaction. So we have something called the differential rate law. It shows you the relationship between concentration and rate of a reaction. Key thing with rate laws is that they have to be determined experimentally. We have to do an experiment in which we're measuring the amount of product being made and how fast it's being made, or we're measuring how fast a reactant is being consumed. Must be determined by experiment. We can't just look at the balance equation and just know the relationship between the concentration and rate. We also call differential rate laws rate laws or rate expressions. A lot of times we just drop that word differential at the beginning. If we hear rate law or rate expression, we're talking concentration of rate, so we're talking differential rate laws. So here we have a generic equation. A is reacting with B to yield X. And we can write a differential rate law for this given reaction. It would be equal to rate is equal to a lowercase k times the concentration of A raised to the power of M times the concentration of B raised to the power of N. So this is your generic rate law expression. Rate is measured in molarity over time. K is your rate constant. This is a lowercase k, or what I refer to as baby k. Not a capital K, because capital K stands for our equilibrium constant. Lowercase k for rate constant. It is temperature dependent. It is constant only at constant temperature, meaning once temperature changes, the rate constant is going to change. Units are super important for our rate constants, and we'll talk more about that later. You're going to have the concentration of A, okay, your reactant. Square brackets, remember, represents concentration. And then raised to the power of M. And we repeat that for reactant B, but we raise that to the power of N. M and N, these are known as orders. These must be determined experimentally. They are not the coefficients from the balance equation. Notice I did not use the lowercase a or the lowercase b. So we're going to do experiments to determine these exponents on our reactants, and we call these exponents orders. We only include reactants into our differential rate laws. Okay? We will not include that product of X. So what do these orders really mean? The orders can be whole numbers, or they can be fractions. So whole numbers or fractions. And again, they must be determined experimentally. Okay. Well, we'll talk real quickly the most common orders that we'll see in our class. Zero order, okay, meaning the concentration of the reactant has zero or no effect on the rate. Meaning if I have rate is equal to K, and we'll just take A for instance, and I raise it to the power of 0, okay, meaning that its order is 0. Anything raised to the 0th power is 1. So this would simplify down to just K times 1. So no matter what molarity I plug in for A, it's always going to be raised to the 0th power, which is always 1, so the rate is always going to be the same if we have a 0th order reactant. Another common order that we're going to see is the first order, meaning the concentration of reactant is directly proportional to the rate. So this means if you double the concentration of reactant, that's going to double the rate of reaction. If you triple the concentration of reactant, that is going to triple the rate. And then finally we have second order. If you double the concentration of a reactant, you're going to increase the rate by a factor of 4, so you're going to quadruple the rate. And this is because if you have rate is equal to K, and let's say we have A again, but now it's second order, meaning its exponent is 2. If you plug in a 2 for A, it becomes 2 squared, and you'll get 4. So the rate is going to increase by a factor of 4. Let's say I plug in a 3 for A. It's going to be 3 squared, and that's going to increase by a factor of 9. Okay, so if I triple my reactant concentration and it is second order, it's going to result in the rate increasing by a factor of 9. Because you're doing 3 squared, that gives me 9. So to recap, differential rate laws are also known as just rate laws or rate expressions. They involve concentration data and they involve rate data. Okay, and our generic equation for rate laws is rate is equal to a lowercase k called your rate constant times the concentration of each reactant raised to some exponent, and those exponents are called orders. One more thing, we can get the overall rate, the overall order of your reaction by adding your exponents together. So overall reaction order would be equal to the sum of those exponents. So in this case, m plus n.